Ready to start. Thanks for returning to our final call of this track in this room. Welcome, Mary, albeit virtually. Hi. So Mary is a security engineer at Zoom, and I'm not sure, I think everybody here will have had that phase in their work life where suddenly everybody's using Zoom. Certainly we at our university suddenly started using that, and end-to-end encryption was one of the features that was widely discussed when Zoom very suddenly became popular, also with us. And then that was, I understand, retrofitted to the Zoom software, and I think there's also a few things that will still be added in the future. So Mary, if you want to start talking to us about what happened and how you're going to do that going forward. I think your microphone is out. Okay, now it's on.
Hey everyone, I'm Mary again, and I'm an engineer at Zoom working on end-to-end encryption features at Zoom. Thanks again to Swiss Cyberstorm for the opportunity to speak to you all today. In this talk, I'll first be describing how we quickly integrated end-to-end encryption, or as I'll be referring to it, E2E, into an existing video conferencing product to achieve properties on par with many other secure communication applications. Second, what we deployed in October is only the first phase of our intended work. Since then, we've been working hard to make verifying the security of a Zoom meeting as intuitive for the user as possible. I'll explain how we are extending our protocol to support cryptographically defined user identities that are externally auditable and backed by a trusted third-party identity provider. Users should know who they're talking to, even without having to trust Zoom. After all, end-to-end encryption is only as secure as its ends. So back in October 2020, 5 months after we first published a white paper, we launched E2E for our video conferencing platform. E2E ensures that no intermediaries can see your communications, protecting users in the case of eavesdroppers and server breaches. And since we've begun our work, E2E has only grown in importance. Now, in case you're not familiar, I'll first briefly describe what a Zoom meeting is like. Zoom supports large video meetings where each participant is synchronously streaming audio-video data sent through Zoom servers to one another. Meetings can include as many as 1,000 people, and users can join and leave throughout. Without E2E turned on, meeting contents are already encrypted by the clients with a symmetric meeting encryption key. Zoom servers do minimal processing of the video streams and therefore don't need access to the plain text meeting contents. However, the server must have the meeting key in order to support some widely used Zoom features, including joining a meeting from a telephone, cloud recording, and live transcription. For this reason, the server generates the meeting key. This trade-off offers important functionality while still protecting against eavesdroppers on the network. But significant risks remain while the server has access to the encryption key. Attackers who gain access to company infrastructure or the underlying cloud provider may exfiltrate highly valuable video and audio data between meeting participants of interest, or even modify server code to gain access to meetings. Here's where end-to-end encryption comes in. In an E2E meeting, only the meeting participants should be able to decrypt the meeting contents. But as you may know, adding security, especially to an existing product, can be challenging. Most importantly, we need to be able to preserve the core functionality of video meetings. While some video services rely on the server to transcode plain text video streams, fortunately, the underlying architecture of Zoom meetings does not require the server to operate on plain text content. So we could relatively easily move key generation from the server to the clients and go from a system originally designed for encryption in transit into one that supports end-to-end encryption. But encrypting meetings with some client key is not enough. Active attacks to gain access to a meeting should be detectable. Our initial release includes new security affordances to help a user be aware of who is in the meeting and can decrypt the meeting contents. Later, I'll go into more detail about our subsequent plans to further reduce the cognitive load for our users. Beyond the core functionality, we also disabled some non-critical features to deliver the initial release, including join before host, meeting reactions, and joining by telephone. While we technically cannot support, for example, E2E in phones, some of these other features, such as meeting reactions, we've since reintroduced as we've outfitted each for E2E use. Throughout, our design and implementation were guided by the goals of deploying an MVP to production as soon as possible, while minimizing implementation complexity and risk, and never sacrificing meeting quality and performance. This sets the stage for our E2E design. We have the existing meeting leader generate the meeting key to send to each user. We already trust the meeting leader to perform meeting administrative functions, and since we can consider the meeting as trustworthy as the least trustworthy participant, we consider this a reasonable and simple design choice that can also scale to hundreds of people. In order to securely send the meeting key to each user, we introduce a couple more keys. First, each user has a long-term key pair. This is a per-device signing key pair where the private key never leaves the device. The user posts their device public key to the server, which stores a directory of user IDs and device public keys. For each meeting, the user generates a new ephemeral encryption key pair. The user signs the ephemeral public key along with some meeting-specific context using the device private key and shares the signed binding of the ephemeral public key with everyone in the meeting. Clients use existing Zoom-hosted infrastructure as a bulletin board to announce keys and other information to each other. In order for a user to join the meeting, the leader computes a Diffie-Hellman shared secret from their own and that participant's ephemeral keys and uses the resulting secret to encrypt the meeting key for that participant. When users join and leave the meeting leader rotates the meeting key to a new random meeting key so that participants can only decrypt the parts of the meeting that they were in. So now when we refer to a meeting participant, we mean a user that the meeting leader has shared the current meeting key with. Meeting participants need to know who they're in a meeting with. In an E2E meeting, we don't want to rely on what the server tells us. So we introduce a leader-driven participant list, which is generated and signed by the leader. Here you can see the leader sending out regular heartbeats with updates to the participant list. In an E2E meeting, the participant list and video boxes that you see in the UI, instead of being server trust, are backed by this leader-driven participant list. This list ensures that all participants see a consistent view of all users who the leader has shared the meeting key with. Participants expect these heartbeats at least every 10 seconds. Recall that the leader should be rotating the key when participants join and leave. So in particular, participants are watching out for these heartbeats so that the server cannot force them to keep using an old encryption key that is known to a recently expelled participant. A client drops out if it misses enough participant list heartbeats from the leader. If the meeting leader changes, maybe because the original leader left the meeting, participants will be shown a leader change notification. The new leader rotates the meeting key and is in charge of updating the participant list. Also, we have a meeting leader security code, which is a hash of the leader's long-term device key that may be read out loud to help each meeting participant detect meddlers in the middle, attempting to intercept the meeting key between them and the meeting leader. Every meeting participant should check the security code with the leader. Note that each new participant joining the meeting must also check the security code. And if the leader changes, then the security code changes and therefore needs to be rechecked. So checking the code can be clumsy. Our future phases of work intend to surface better user identity information that will make this check less necessary. We've now described the E2E design, which includes the meeting key messages and the participant list heartbeat messages. Next, I'll describe some performance-related details that affected our implementation. While we are streaming megabytes of video data over UDP, these new messages we've introduced to support E2E are sent over a reliable TCP channel, and our protocol needs to be performant on bad networks and old, cheap phones. Of highest priority is to make sure that joining and staying in a meeting is as easy as possible. This means getting the meeting key. Especially because we're working with synchronous audio-video data, we want to get meeting keys to all the participants as fast as possible, and then rely on reasonable timing thresholds for the participant list heartbeats to enforce security properties. You could imagine a protocol that couples rekey and participant list messages together to enforce a tighter rekey property, but it was advantageous from an engineering perspective to not build in a stronger dependency in order to reduce the risk of bugs or of affecting meeting performance. Also, to reduce spikes in meeting key traffic, we throttle rekeys such that the leader might not rekey for every participant join and leave if they happen within a short period of time, but will rekey within 15 seconds. Joins and leaves happen more often than you might think, especially at the beginning and ends of large meetings. We also had to determine the frequency for our participant list heartbeats. On one hand, the participant list in the UI should update frequently enough for a reasonable user experience, while on the other hand, sending too many heartbeats would produce overwhelming network traffic, which would also affect the user experience. And whether it's a new face in the participant list or a new leader, these changes in the UI need to be noticed and reviewed. This can be especially difficult in large meetings. With every notification that we expose in the product, we also consider its potential to contribute to alert fatigue. Designing a protocol is only the first step. We also had to implement and deploy our changes in time for our October launch. Clearly delineating the separation of concerns between various components has been crucial to our execution. For the client-side changes, our engineers built a new library that takes care of generating the meeting key and the leader participant list, which exposes a small interface that the rest of the Zoom client code uses. We've carefully designed the interface as it's very hard to change once we release it. Next, clients post their device keys to what we call the key servers. In subsequent work, which I'll be describing next, clients may start posting additional identity information to these key servers. We built these key servers to be as standalone as possible. This means thoroughly understanding how user and meeting data is already managed by the existing Zoom servers, minimizing the key server's dependency on this data, while also implementing checks to ensure that all data assumptions and constraints are satisfied. Lastly, though we require clients to upgrade versions in order to begin to use E2E meetings, we in general try to avoid client changes that are backwards incompatible. We're now in progress implementing our subsequent plans to make it even easier for meeting participants to verify the security of their E2E meeting. Here we introduce the second big question that our work intends to solve. How do you know who you are in a meeting with? In the remainder of my talk, I'll describe how we'll make it easier for users to confirm that only the meeting participants that they expect and trust are in the meeting and can decrypt its contents. To this end, it definitely helps if you can see and hear everyone in the meeting and you check meeting leader security codes. But in the worst case, cameras and microphones are off, or you've never met some of the participants before. Additionally, participants can rename themselves. Of course, different E2E meetings have varying user privacy requirements. In some cases, a self-selected and server trust display name is completely adequate for identification. And in some cases, we welcome the creativity. In this case, you'll want to check meeting security codes to detect any server interception of meeting contents. But because this check, as I've previously described, can be cumbersome, we want to build additional features that rely less on the security code and make verifying meeting security as effortless as possible. So, how do you trust that a device key is associated with a particular user identity? And relatedly, how do we expose those notions of user identity in the product? We are now building a notion of multi-device user identity, which supports a more human-friendly and usable notion of identity. And this identity will be committed in an externally auditable transparency tree and may be backed by a trusted third party. So this user identity includes a set of devices, like a laptop and cell phone, and their device public keys. And we introduced two unique human-friendly identifiers to represent the user's set of devices that may be displayed in a meeting. This is your email address that you use with Zoom and a domain name for the account that your user is a part of. To quickly highlight this particular concept in Zoom, users may be part of an account, likely for their company or school. Because users in the same account may have different email address domains, the account's admin will need to select one unique domain name, or ADN, for the purposes of identifying the account. These user identifiers are mutable, but they must be associated with at most one user at a time. Now presented with this information about Alice in a meeting, each of the other meeting participants may verify Alice by essentially asking these two questions. One, have I seen this user and or this device before? And 2, do I trust the email and ADN associated with this user? It's important that each meeting participant and client does the work to verify Alice's identity information instead of relying on the server to be honest. To answer the first question, we will implement a contact sync feature where clients remember their meeting participants' device keys and display an alert if the meeting participant's device has never been seen before. This trust on first use, or TOFU, warning is a fairly common security UI feature in chat applications when conversation partners reinstall their app or switch phones. But alert fatigue significantly undermines the security of such a feature. If you're a programmer, how many of you have seen this TOFU warning in your terminal before, and how many of you found it more annoying than it is scary? We observe that it's not uncommon for users to get new devices or have multiple devices in use at a time. We'd like to reduce the number of necessary warnings and make them more meaningful by using our construction of multi-device user identity. Here, we introduce a device approval process. When the user registers a new device, one of their older devices may cryptographically approve the new one. Relatedly, devices may be revoked if they have been lost, stolen, or just not in use anymore. You can now imagine representing a user's identity with an ordered sequence of actions like this. I'll be returning to this idea in a moment. Back to contact sync, by establishing trust between a user's devices, we can now minimize the number of contact sync warnings. The resulting UI is one that is user-centric rather than device-centric. Now we've seen how a user's identity changes over time with device approvals and revocations, along with other actions like setting and changing one's email address and joining or leaving an account. How do we actually represent this and ensure that everyone sees the same current state of every other user's identity? We store this information in an append-only list called a sigchain. Each action on a user's identity is stored in a sigchain link, each containing a hash of its preceding link. These user identities will then be committed to a transparency tree, which is built on top of a Merkle tree. The hash of the tree root commits to all Zoom users' identities at a given time. The transparency tree is hosted by Zoom, and it is externally auditable in a privacy-preserving way. This further prevents the server from forking a user's sigchain. In other words, showing different versions of the same sigchain to different users. Because all changes made to a user's identity must be committed to, any server misbehavior will always be able to be detected. Our Zoom transparency tree is similar to the project's certificate transparency, keybase, and seamless, but not completely. You can find more detail about our transparency tree in the white paper, but to really quickly illustrate what it does for us, consider the basic attack where the attacker somehow adds a device to Alice's identity. This can happen if the attacker successfully guesses Alice's password or if the attacker compromises the Zoom server. The attacker can now join a meeting with Alice's identity. But the transparency tree and auditors ensure that the attacker cannot cover their tracks and erase the device that they've added without violating the consistency and append-only properties of the tree. And when Alice comes back online, she should review any changes made to her identity and notice this new unexpected device. Now with sigchains and the transparency tree, we can also help answer that second question. Do I trust the email and account domain name shown for this user? There's actually two parts to this question. First, do I, the human on the call, expect to be speaking to someone with this particular email address and ADN? And do I think that those identifiers are trustworthy? For example, I should be suspicious if I see the Alice on the right with the unexpected ADN company with a zero.net. Second, having established that the email and ADN are reasonable, how do I trust that the ADN in fact authorized Alice and her email address? The Zoom server stores this information, including account membership, that is essential for establishing trust. But we commit this information to the transparency tree, so account admins and members can review and detect any and all unexpected changes. As they say, sunlight is the best disinfectant. But in addition to transparency tree-backed identity, whereby ensuring the detection of misbehavior may de-incentivize attacks, we'd like to introduce another feature that can prevent impersonations in a meeting. This feature allows users and accounts that use an identity provider or IDP, examples of which include Okta or Google, to have the IDP independently attest to a user's identity. Here we leverage the fact that many of our users already trust their IDP for identity management and authentication, and therefore may also use the IDP as a trusted third party to vouch for a user's identity in a meeting in a way that the Zoom server cannot tamper with and that other meeting participants can verify. I'm excited to say that we plan on releasing IDP-backed identities by sometime next year. Here are the high-level pieces. First, the account's ADN publishes a delegation of trust to its particular IDP in a way that doesn't rely on the Zoom server. And the designated IDP signs identity attestations for users in that particular account. Next, I'll describe the details of how Alice obtains an attestation and then how Bob verifies Alice's attestation. To support identity attestations, we will partner with IDPs to implement an extension of the OpenID Connect or OIDC standard to allow a user to make claims about her identity that are signed by the IDP. First, Alice authenticates to the IDP using OAuth. Our authentication flow ensures that only the user's client and never the Zoom server can make changes to the identity that the IDP is attesting to. Then Alice posts a snapshot representing her identity to the IDP. For example, the snapshot can contain information such as the SIG chain tail, which commits to the current state of the user's identity. But for our initial release, in order to independently release IDP attestations from SIG chains, the snapshot will be of the device key that the user is joining the current meeting with. Finally, in a meeting, Alice will request from the IDP her identity snapshot signed by the IDP's OIDC key. We call this an attestation of Alice's identity. Other meeting participants will then verify Alice's IDP signed identity. To do this, other meeting participants need to confirm which IDP is allowed to vouch for Alice's identity. This is what I was referring to previously, where the ADN must delegate trust to the IDP. Though the Zoom server and Alice do tell Bob what Alice's IDP is, we need to get that value from a trusted party. This is Alice's account, and it's at ADN company.com. We plan to implement this using DNS text records where the admins of company.com configure a DNS text record containing the value for their IDP domain, in this case, company.idp.com. So the first step of Bob's verification process for Alice's identity is that Bob's client will request company.com's DNS text record to confirm Alice's IDP domain. Then Bob's client will fetch the IDP's public signing key at the standard path for OIDC keys. Also not represented in this diagram is that all requests to other users' IDPs go through an HTTPS proxy that hides the client IP from others' IDP servers. Bob will then verify the IDP's signature in Alice's attestation, as well as that the attestation and the user identity as stored in the Zoom servers match. To re-emphasize an important point, Bob needs to see and trust not only the email address displayed for Alice, but also the ADN for Alice's account. As an example, say I trust the admins of the ADN bank.com, but if I see in a meeting a user with the ADN evilbank.com that vouches for an email address that looks legitimate, say CEO at bank.com, then I should be suspicious of that user. Now back to these two questions again. I've described SIG chains, the transparency tree, contact sync warnings, and IDP attestations. These various mechanisms all help a user answer these two questions to verify others' identities. While they complement each other, they don't cover exactly the same things. There's a lot going on, and you might be wondering, for example, when should I be relying on contact sync versus IDP attestations? Or when should I rely on the transparency tree instead of the IDP? Contact sync, where clients remember device keys they've seen, is a solid first step in pursuing client-verified meeting security. But when you've never met your meeting partner before and you see a trust on first use style wording, it can be especially helpful to require an IDP-backed identity to confirm the user's email address and account. This use case may be more common than you think. Maybe you're on a tech support call with your cloud provider or connecting with someone in your company's HR department for the first time. In both cases, you'd like to confirm that you're talking to an actual employee at the expected company. But IDP-backed identity is not only useful when meeting people for the first time. If a user leaves or is fired from a team and you meet with them again, you should be able to confirm, even if the user attempts to use the same meeting key again, that the device key is now revoked or is associated with a different email address and ADN that don't belong to that user's former employer. Another particular benefit of requiring users to present an attestation in a meeting is that it can prevent impersonations. Even if an attacker gains access to Zoom servers and modifies a user's identity there, the attacker won't be able to authenticate as the user to the correct IDP and get a valid attestation. However, not everyone uses or wants to use an IDP. In that case, or if the IDP itself has also been compromised, the transparency tree will allow for the detection of any misbehavior. In addition, the construction of multi-device user identity lays the foundation for applications beyond context sync in meetings that require syncing encrypted data between trusted devices. So now I'll finish the talk with a couple of takeaways. The security of E2E depends on knowing who is at the ends. Starting with a user's device public keys, we've constructed a human-centric notion of Zoom user identity. In our multiple phases of work, we aim to offer various options to make identity verification more effortless for the end user while minimizing the need to trust the server. Building E2E in the real world, especially for an existing widely used application, has presented particular challenges. From day one, our design and implementation choices and the resulting security properties must account for existing architectural constraints and performance requirements. We plan on releasing features in multiple phases. Just as we did with the MVP, we want to offer the best security guarantees possible as soon as possible. But as always, the complexity of introducing new features and versions requires careful review and testing to ensure that compatibility between versions doesn't introduce vulnerabilities. Lastly, I hope this talk conveyed how the possible security levels for a meeting in fact lie on a continuum. And beyond the formal security properties, the practical effectiveness of the feature depends on how it's conveyed in the UI and understood by users. By making the end user experience top priority throughout our design and implementation, we aim to deliver ET properties that protect our users as effectively as possible. Thanks for listening. Please check out our white paper for more details on what I've discussed today, and I'm happy to take questions.
All right, thank you very much for the presentation. Are there any questions from the audience? Yes, someone in the background. Maybe could you place yourself so Mary can see you?
Hi.
Yeah. There.
Thanks for the talk. Very nice to see the end-to-end encryption finally coming to Zoom. And it was very nice to see the white paper on GitHub and put there for public review. My question is whether end-to-end encryption will ever come for the web, well, connecting via a web browser to a Zoom call.
Great question. So as you know, it's currently not available. We've been discussing it since the initial release about ways that we could offer it. That's all I can say at the moment. We are definitely thinking about it because we understand that a lot of our users do use the web client.
Yeah. Okay, thanks. That was my first question. And then the second question is about this IDP integration. You were mentioning working with major providers like Okta or Google. Will the specification be public, and so that, for example, those of us that are doing IDPs on-premise with open source, we could implement the specification?
Definitely, our intention is to publish an API spec that any IDP can implement and therefore integrate with this attestation protocol.
Great.
So yeah, great question.
Thanks a lot.
All right, thank you very much. Are there other questions for Mary? Oh, sorry, behind me, yes, please.
Thank you for the talk. So I wanted to know if you had any bottleneck issue from the performance point of view using the cryptographic algorithm you choose, because I know you used EDDSA and X250, 5519 as algorithms, and these are typically extremely fast, so they should be able to support thousands of operations per second, like many thousands. So you mentioned the fact you were throttling to like 15 seconds, stuff like that. So what was the bottleneck?
Yeah, I would say that cryptographic operations were not the bottleneck for our performance. When we tested our when we tested our protocol with large meetings, the main challenge is network traffic, which is kind of what I described. The fact that the clients need to be processing or sending and receiving all of these messages. So that's where the challenge was.
Amazing, thank you.
All right, thank you. More questions? Yes, there's two. Brilliant.
So thanks, this was cool talk, but you seem to base a lot of the thing of kind of this verification thing on DNS, but if you don't have DNSSEC turned on, it's kind of easy to fake this. Is there a plan to kind of at least show the user, hey, we're not really sure you talk to the right IDP?
Yeah, originally, if you see our current version of the white paper, we actually say that we wanted to host a page on the subdomain that belonged to the company, but after discussing internally, we were concerned about how much setup requirement it would take for the admins of the account to set up, which is why we decided to use DNS. And the additional check that we're doing is that not only is the client checking the DNS record for the IDP domain value, we are also having the Zoom server, as well as Alice, if Alice were the user you're verifying, provide that value as well. And the important thing is that all those values must match in order for the IDP domain to be considered valid. So that's where the check comes in.
All right.
Okay, there's one
There
more.
was one.
Hi, Mary.
Next.
Thank you very much for the talk. Maybe I didn't understand completely, but I expect that once E2E is implemented completely, Zoom will not have any chance anymore to tap into my Zoom meetings. Is this true?
So that is already the case right now with what we released in October 2020. As I described, the most important thing is that you need to check the meeting security code to ensure that someone in your meeting that you see in the participant list is not having all their traffic being intercepted by a meddler in the middle. It is already the case that the client keys the keys for the meeting are generated and shared completely on client devices. They never reach the Zoom server. But the important thing is you need to be able to check for MITMs, and that's where most of the subsequent work is focused on, making that check easier for the user, so that doesn't require as much effort to do.
This is understood. I'm not talking about third parties. I'm talking about Zoom as the provider itself. So that Zoom itself, by directive by a government, for example, cannot intercept my meeting. Is this something I can get in writing, having a contract with you? And can I have the source code of the apps to verify that this is implemented in a thorough fashion?
Right. So to your first question of can you not have this traffic being intercepted by Zoom, maybe I'll try to clarify. Traffic will go through Zoom's servers. The video traffic will go through Zoom servers, but it is now encrypted with a key that never gets to Zoom servers. So in that sense, Zoom servers will never get the plain text of your meetings. That's already the case.
So I come to the second question once more. So you're pissing off the US government, more or less?
Well, then you can say that about any provider who is offering end-to-end encryption.
Unless they have some backdoors implemented, which nobody is aware of. So that leads me to the second question. The apps installed on mobile devices and end devices, is this software to be made open so people have can have a scrutiny on the code to verify?
So that's something that I have less purview over. We do rely heavily on internal as well as third-party audits of our code, but I cannot say if any of that will be made openly available at any time.
Would be a bold and great step if you do that. Thank you very much anyhow.
Thank you.
Thank you very much. Are there any other questions to Mary? Because otherwise I've got one myself. So I understand that your E2E encryption is now default. Is that the case? I don't need to do anything as a user.
That's actually not the case as of right now. So you need to turn on this feature.
Right.
There are instructions online that will be able to describe that in more detail, but you need to enable it for your user. And then for a particular meeting, you need to make sure that it is turned on. And the way that you can ensure that it has been turned on is that in the top left corner, there is a green shield with a lock in it.
Okay, thank you. And second question, I mean, there are existing protocols, like for instance, the Signal protocol, and it seems like, at least for the identity management part, you're implementing your own bit. Is there a special reason for that? Was that not suitable for you?
In every case, we have considered the available protocols for use. And in particular, double ratchet, it's great for asynchronous communication.
Okay.
But for our synchronous case, we thought that it would not be performant enough to use, especially because we're trying to scale to 1,000 participants. Sure. For the identity management stuff as well, we have considered available standards, but none of them satisfied our security and privacy requirements. And so that's why we've designed what we designed.
Okay. All right, thank you. There's one more question. I'm sorry, Mary, are you okay for time?
I am okay. Yeah.
All right, super.
So one last question from me. Is end-to-end encryption available worldwide in all jurisdictions? And for example, is it available in China, or is it a different implementation? Or
we have this one implementation. To my understanding, we've deployed it and made it available everywhere. I am not aware of any exceptions to that.
okay, thanks for that.
All right. Okay. That was pretty much one question for everybody on average. Brilliant. Brilliant talk. Thanks for the details. And with such a popular software as Zoom, I'm sure we understand the responsibility that you have for keeping it secure, but also available and stable. That's certainly not an easy task. Thanks again from the audience. Maybe we have another round of applause. If you were here, we'd be giving you some Swiss chocolate. We're sorry, we'll have to keep it until you make it over at some time. So accept our gratitude, and thanks. Have a nice afternoon.
Thank you again for having
Thanks.
me. It would be great to visit one day.
All right, super.
Thanks.
Thanks.